Hey, welcome to HTM Hackers Hangout. It's March 2nd, 2018. I have a list of topics that I want to talk about on our forum that's linked in the description if you want to follow along. I'm going to talk about this MIT AGI course that's going on, and then I'm going to talk about some documentation and some community stuff. We'll talk a little about Unity. But somebody brought up something they wanted to talk about first. I hope you guys don't mind. Unless Lewis, do you need to leave? Because we can talk about it. Okay, so I'm going to get a little philosophical here because someone was asking about innateness, and this is a big topic in AGI right now. When we talk about innateness, I put some notes on the board. But so I've been reading papers on this. Specifically, there's one called "Building Machines That Learn and Think Like People." This was released last year, and it's big names like Josh Tannenbaum was on here, Tomer Ullman, Brendan Lake, and Samuel Gershman. And they kind of, I think, do a good job of defining what innateness means when people like, I don't want to speak for Gary Marcus, but he talks about innateness a lot. But the way they talk about innateness is basically, what do you need for AGI or for truly intelligent things? What do you need to be pre-wired or baked in? What a priori knowledge needs to exist in the system in order for it to be intelligent? And the examples that they give are like, we need to bake in things like knowledge of number systems, space, physics, and psychology. And they use terms like they need some form of intuitive physics, intuitive psychology. And then they discuss a lot of ways in which you can see in humans that innate knowledge exists. However, in all of their arguments, they're pointing towards young humans, but not babies. So here's the thing. The issue I always take when we talk about innateness is, yeah, you do have to build up knowledge of number systems and space and physics and psychology, of course. But I don't think any of that has to be inherent in the system before it starts learning. I think those things are some of the most basic constructs of reality that an intelligent system has to learn, just like a newborn human. It doesn't know right away what numbers are, what space is. It doesn't even have a very good definition of self, of boundaries between reality and self. That's why babies make lots of random movements and they're constantly getting feedback. That would say the first few months of life are really just trying to figure out, what am I versus everything else? Where is that boundary? When I move, what do I affect? How does it work? All of that builds up a model of reality that includes things like space and physics. I think that's sort of, I'm gonna mute Clay. Okay. So I don't really think that from an HTN standpoint, we would say that we require this type of innateness for intelligence in an HTM system. But what I would say we have to have pre-wired for HTM to work, and this is stuff that I think we're actively working on, is we have to have an intelligence with the ability to take action and affect reality. So there has to be some sense of a world that it can play in, a world that it exists in, whether that's truly reality or not. I'm just saying reality in quotes. It has to be able to take action in that reality and affect it. And generally, when an AI is embodied in some way, it is a part of the reality that it experiences. Our bodies are a part of reality. So an AI agent, when it takes action, if it can perceive also, that's the second thing, you have to be able to sense changes to reality over time so that you can tell what actions had what consequences. Aside from that, I'm not sure you need to pre-wire anything else. And what you're doing when you have these abilities is you have an ability to learn. You're basically pre-wiring learning. If you can give a positive feedback signal to the agent so that when it properly predicts what in reality is going to happen when it takes actions and it gets positive feedback for that, we're teaching it to learn. it gets positive feedback for properly predicting the future when it moves or takes some action. And I think at a very basic level, that's the main requirement. That's the only innateness that I would say would be required for an HTM system. Is now, that being said, I haven't run this by the whole research team or anything, but I think they would probably agree with that. We're not trying to research any of this, like how to bake in this type of stuff. We think the brain learns this stuff. We think all this stuff is learned. I mean, it's true. And if you look at a lot of the psychological research on children, they do have a lot of innate knowledge, but it's after being alive for several, years or months, or they have had a chance to soak up all this reality and their interaction with it. So yeah, they know when you move something behind something else, it's still there. They know that because they've seen that so many times. It's not an innate knowledge. They've experienced that. A newborn baby can't do any of that stuff. It's just, flailing, just trying to figure out what it is versus everything else in the world. So that's my take on innateness. And there was another question about dendrites. Oh, so I was just looking. Mark Brown, which is BitKing, just saying he can't join. That's a bummer because I was looking forward to discussing some things with him. But all right, so let me talk about dendrites. Mike 2.0 on the forum was asking about dendrites. So I'll try and break this down. So here's a cell body. Here, these are like apical. Let me get rid of this. I'm going to draw a neuron. Let's say we've got some apical dendrites up here. I'll label these better. Distal. Well, these are called basal dendrites. And typically, what Jeff has told me is a pyramidal neuron will have 4 to 5 dendritic branches coming off of the cell body, something like that. And each one will branch 4 to 5 times, and we've got like an axon coming down here. So axon, and this isn't perfect, but apical dendrites, and then all these others, all of these down here that are not apical, that sort of go off laterally, are called basal dendrites. We don't use that term a whole lot because we split them up. We say, okay, up into this first branch, these are proximal. So all the close ones, that's what proximal means. Those are proximal dendrites, and all these other ones. What colors do I have here? All these other ones out here, beyond that, all these other basal dendrites are distal. So that's the difference. And we don't talk a lot about apical dendrites. We know those will be necessary once we start talking about creating about attention and creativity and stuff like that. That will come into play. But right now, our theory, we really focus on the proximal and distal dendrites within the basal section of the pyramidal neuron. Another question: how does HTM model neurons? Are they summing machines or classical neural networks? So I would call them they're neural networks, definitely, because they require, it's all about the weights. We don't call them weights, we call them permanences, but it's basically a Hebbian learning type of neural network, which deep learning systems are not Hebbian systems. And most current people that are working on AGI in the deep learning arena don't have much faith in Hebbian learning systems. I'm starting to understand as I read more. But HTM is a Hebbian learning system. And currently, there's no biorealistic time component. We just take input like one after the other, and we're not doing any timing. And there's a video about this where I talked to Jeff about spike timing and oscillations and stuff on our YouTube page. I think it's called Exact Timing and Oscillations. So you can search our YouTube page for that, and we do discuss that. We don't model, well, how do I say this? All HTM neurons are pyramidal neurons. And we do, the way we group them is we'll group them into layers, or and we may eventually group inside of a layer. We might have different groups for different like grid cell modules or something like that. But they're all pyramidal neurons. There are other types of neurons that are incorporated in the model that are inhibitory neurons, but we don't model those directly. Like, we don't create instances of inhibitory neurons. What we do is we've noticed the effect of inhibitory neurons from experimental neuroscience, and we just model the effects of inhibitory neurons. So we only directly model pyramidal HTM neurons, and the inhibition is done in a more simplified way based on what we think we know inhibition does. So I hope I answered that. And his last question is, how do you measure that changes to HTM are useful? So examples, if one of our researchers reads a neuroscience paper on a new way to do something and it was implemented in HTM, how do you test that those changes were useful? Well, we've got lots of tests that we run, and we have benchmarks. So at this point, we don't change the core of HTM theory often at all. Like, I don't remember the last time we changed one of the core, ideas of HTM, which is the distal dendrites put the cell into a predictive state, which makes it fire faster and inhibit its neighbors when it gets proximal input. That is like the core of HTM theory. Now in NUPIC, the core code algorithms haven't changed in years, as far as I know. Now we do all of our messing around with that theory in our research repositories because we have the flexibility to do that there. Because we know that we told the community, don't depend on this stuff because it's in flux. But NUPIC is stable. Those algorithms don't change. But in the research repositories, that's where we do all of those new experiments. Like, a new way to do synaptogenesis would be done in the research repository, and we would fully vet that out so that logically everyone agrees that yes, that's the right way to do it. And prototypically, through these experiments and demonstrations of it is actually working the way that they think it's going to work. And even then, it's going to take a lot of vetting to get that into the official code base of NUPIC. Okay, last thing that Mark Brown is asking, I was thinking about this. I don't know if I can answer this, Mark. He asks, how does a field of HTM neurons recognize a complicated pattern that's represented to the entire ensemble at the same time? And I keep thinking about the spatial pooler, perhaps, because each column in the spatial pooler is just looking at a portion, a section of the input, and is only after a good amount of learning, is tuned to look at just specific features in that portion that it's looking at. So it has an affinity towards specific features. The ensemble of all of those mini columns that are at work together to identify these different features and how they occur over time and which ones occur in what orders and stuff. But it's sort of hard to say how that works or how it recognizes a complicated pattern. I mean, it's the distal segments and synapses that tie those spatial features and all those represented in lots of different mini columns together over time. So what ties that pattern together are the distal connections, while the proximal connections are what sort of lock in what mini columns are going to respond to what spatial features. It's hard to answer your questions about a partial match versus a completely novel thing. I don't know. I think I could put together some experiments, but honestly, I don't think I have time to do that. You're welcome to. Okay, let me address some questions now. Mike is obviously watching. He says, with regards to innateness, sounds like I lean towards mostly learned and not much innateness. It's referencing Gary Marcus's book. I'm not saying that the baby's mind is a completely blank slate, but we're leaning towards not baking in anything until we know we have to. And at this point, we don't know we have to. So any pre-optimization, what I would call it, of trying to bake in these ideas of innateness are just that. It's a pre-optimization. And with the sensory motor model that we're working on, we're trying to make work without those things. We think as far as neocortex is concerned, there's something general enough in neocortex that it can start learning sensory input based on motor commands and put together models of things in reality without having innate knowledge of characteristics of the universe or reality, as you might say. Okay, I have other things to go on. How does HTM model neurons? Heavy learning? Yeah. Mike, I'm going to respond to you probably later on the forum, so I'm not taking up all my time on just your questions, because there's some other things I want to talk about. So let me go on to this MIT AGI course, and this is sort of just a personal thing I'm interested in. I'm going to share my screen. There's the Hackers Hangout. Hopefully you can see this. So here's the MIT AGI course. You can see it at agi.mit.edu. And they've got some interesting guest speakers. Oh, there's another Stephen Wolfram. The video of Stephen Wolfram just came out, so I need to watch that. I've watched all of them except Stephen Wolfram. And I've been a bit critical of this on Twitter, just because there's only one neuroscientist involved here, and that's Lisa Feldman Barrett. So mostly I'm critical because I wanted Jeff to be in this panel. And I said so to Lex Friedman. You know, I don't know why Jeff is in this list of people, because we have a lot to say about AGI and how we think intelligence works in the brain, and that seems to be what a lot of these guest speakers are saying too, is that we need to look in the brain and understand what's happening there and try and figure it out, especially Ray Kurzweil, who said exactly that. He even referred to the neocortex as the shape and size of a dinner napkin, which is an analogy that Jeff made up 10 years ago. So yeah, we totally agree. So why aren't they talking about the work that we've been doing for such a long time? That's basically my critique. My plan with this is, because we were not invited to be a part of this conversation, is to I'm going to write not necessarily a rebuttal, but a response to these guest speakers in probably a series of blog posts that I'll be posted to numenta.com or .org. I don't know. I really liked Lisa Feldman Barrett's talk, actually, and which was interesting because I got into an argument with her on Twitter beforehand about emotions, and I didn't think she agreed with me, but I think she does. I think we do agree. That's the thing about Twitter, you know, you never really know. But her talk was I thought really lent towards the HTM way of thinking about intelligence in the brain, which I really liked. So I encourage you guys to watch these, even though it doesn't include Jeff's point of view. I would love to give MIT feedback on these lectures, and if you guys want to do that, that would be awesome. So let me talk real quick about some documentation. You guys may or may not know about BAMI. So I have a personal mission at Numenta that I don't know if I'm going to achieve or not. I want to turn this whole BAMI thing, this BAMI document, which is right now just a series of PDFs, into a web document that basically says, here's how to build HTM. Here's how to build HTMs. Because there's a lot of people trying to build HTMs, and anybody that has questions about it, I always point them to BAMI. But the way this document is structured, it's sort of how to build HTMs, but at the same time, it reads like a scientific, technical document. And I think that I think we can do better. I'd like to make it better. I'd like to make it a completely web resource so that we can reference sections to each other better. So I'm trying to work on that, and I'm interested if anyone has feedback. If you've read BAMI and you have critiques about it, if you like PDFs and you're like, no, don't make it non-PDF because that's my plan, I don't want it to be a PDF anymore, then you should let me know, because that's what I'm going to try and do. I'm fighting about that right now. I would like it to be a web resource. I think it would be much consumed much more often, and it would be easier for me to link to documentation when somebody says, hey, how do you make a spatial pooler? I don't have to say, download this PDF, look at section 5.1 and paragraph 2. I can just say, here's the link, which is much better. Okay, what else? Okay, getting rid of Slack. I don't think we need a chat room anymore. Now that we have discourse, discourse is just amazing. I love our forum. It's such a good communications medium. I really don't think we need a chat room. It's just one other place that I forget to look in and go find people who are trying to talk to me. So I think I'm going to get rid of Slack. I already got rid of Gitter. I don't think I got rid of it, but you know, maybe I did. But I think I'm going to get rid of them. So all communication will come to HTM Forum. There will be no chat. If you want to have chat, I mean, it's pretty much a live chat in HTM Forum some days. So I would say go there. I'm looking for feedback if anybody's like, oh, please no. But honestly, hardly anybody's ever in there chatting. And usually I forget to go there too. All right. The last thing I think I'd like to talk about, and thanks, Lewis, for sticking through 20 minutes of me rambling. People have been asking about how we use Unity with HTM, and I was hoping that Lewis has done pretty much all the work on that. Maybe you could describe the methods you used to hook NuPic up into Unity so that it could be attached to some like rigid body structure in Unity. I'll let you do that.
Thank you, Mark.
Yes.
Okay. As you know, NuPic is Python-based and Unity is C#, so they don't talk to each other very easily. So the way I usually implement, I use Unity to do all the UI and the 3D environment and everything that has done in an environment point of view, and I create a Python command line interface to the algorithms, and use C# to communicate to the Python process via standard I/O, just like, you know, a command line interface. So this way I can just work on Unity independent of Python or any other limitations that I have between the communication between Python and the C#. So let me share my screen and I can show you what. Let's share my screen here. Let me share.
Need help sharing? I think I can do it.
I think I found it. Okay. So the first step, I don't know if you can see my screen.
Yeah.
It's you know, the first step, you know, this is an internal project that we have that we use in one of our papers for the, it's a layer and colors, I forgot the name, layers and column papers, which you create, we run experiments where we have a robotic hand trying to identify objects. So you have different 3D objects and you have this hand, and we try to identify those objects. So we use Unity to run those experiments, for example. And one thing, for example, we did is here's a spatial polar interface. So we create a command line interface to the spatial polar. This is pure Python. That it just does that. So this is the whole interface. So it creates a spatial polar with those parameters, and then passes some training data, and then just run the inference. And the actual code is basically create a spatial polar with those parameters, and just fit it. There's no much coding here. This is it. This is all the code for that. To link that to Unity, we need to interface that with Python. So, and that's a C# environment. So in that world, it's a whole different threading model, whole different, everything is different. So to avoid that, we just use the Python as a external process, and we communicate via that interface that I just showed before. And it's basically, I create the Python process and attach the output, the standard output to that process. And once I receive a message from the standard output, I just forward that to Unity. And it's basically sending asynchronous message to Unity, and you know, and sending and writing to the text, writing to the external I/O of the Python process. So that's basically the interface. It's a external I/O back and forth between between C# and Python. So this is, for example, like, you know, to read the content and so forth. This is the whole interface between that. So the interface you can actually find here, which is one of a different project that we created for fun. That's our internal hackathon we did. And we can see this interface in here. So it's accessible. We can see that today. And to use that in a actual process, in actual algorithm, this is a wrapper to that Python process. We use this Python class that I create, and I just give them the Python script that I want to use, and I just attach the methods to the external I/O. So every time we receive something, this will get called with the information. Like I send a write training data, or receive, or I can just read the line, read the actual content. So this is basically the whole interface. One caveat is this is it's a blocking call. So you probably want to do that in a coroutine, so it doesn't block your UI. Your UI is not blocked. So you're using a coroutine to update UI. You run this as a separate coroutine process. So this way, this is it. This is how the interface. So first thing, install Python, create a Python command line interface to the algorithm, then use this class, the Python class that we have available here, to wrap your class, and then use a coroutine to feed data to the algorithm and update UI. So that's those are the 3 steps we use usually for Unity.
Thanks, Louis. If there's, we've always planned on making this open source. There's a little red tape we got to go through to do that. So if there's enough interest, if people really want to see this, let me know on the forum or PM me or something, and maybe I can make it a higher priority.
So part of it's already open source. Like the Python interface is open source, and there is an example algorithm in there. So it's just the other algorithms and the Think project.
Yeah, and this is, it's not like our experiments are still open source in the research repository. It's just sort of the glue code between Unity that includes like the robot hand and stuff.
Correct. Stuff that's not GPL.
Yeah, so we need to figure out what kind of skin we need to use a skin that's the right license. You didn't know you could license skins, but you can't. Thanks, Louis. Okay, well, I don't have anything else to talk about. So I see we've got a guest, Rashi. If you have anything to say, you should unmute yourself and let us know if you have a question or anything. We'd be happy to discuss. Otherwise, I don't think, I'm looking at the forum post, and it looks like Mike is responding to a lot of things, sort of summarizing what we said, which is great. Thanks, Mike. And otherwise, Glenn, do you have anything you want to talk about? You're always working on something. You say eventually you'll talk about it.
Right. It's still too soon, but it's so exciting and it's coming along so well. I will have a present for you someday. That is so great, but it's still going to be a little while.
Okay, fair enough. Okay, Rashi, I can't hear you. I see you're unmuted, but I can't hear you.
Hello?
I can barely hear you.
Oh man, I think it's on my phone microphone.
I got it. I hear
I'll try talking like this. So, and I just saw that you were streaming, so I thought I'd tune in. I'm sort of newer to the HTM model. I watched a few of the videos. So I have sort of a more rudimentary question, which is like, I'm starting to grasp the idea of mini columns, and I realize the terminology has changed, which has been making it harder. But broadly speaking, do you think you could like illustrate like what that looks like in terms of the neuron arrangement? I know it's groups of neurons, but you know, sometimes it's hard to visualize the shape of it.
Yeah, I can tell you what I know. Hold on, let me. I've got. Oops. I'm trying to turn Lewis off. I don't know how to do this. Stop presenting there. All right. So this is something I would like to talk more to Jeff about, because you can see mini columns in some places. Like I know in mouse cortex, you can actually see it. Like you can see the cells are kind of grouped, you know, through the layers in these structures, and they're not all exactly lined up, but you can sort of group them like that. But in other places, you can't see them, but they're still there. And I don't know exactly how that works. But from what Jeff says, is it's not. So if you look at a column and all of these layers, there's some layers that have many columns, and I don't know which ones exactly are which. Some layers will have many columns, and the many columns will span layers. Like they'll continue through, you know, layer 3 and layer 4. I don't know if those are the right layers, but they'll go through different layers, and so we can see examples of that. And we don't know exactly what the functionality of that is, although that's an active research topic. I hear them talking about that often. And there's some layers that don't seem to have mini column functionality, which we assume means they're not doing something that's like spatial pooling, because we know that the mini columns are enable spatial pooling. You can't do spatial pooling without these mini column structures. So they may be doing something else. We think they're doing another type of pooling, this type of temporal pooling over, and generally you'll have like a pooling layer on top of one or two other layers that might have mini columns, and we're still trying to figure out exactly why. Now, physiologically, I don't know. That's something that I've been wanting to ask Jeff, but every time I go to the office, I have something different to ask him. So I'll ask him, because I know he knows, physiologically how these mini columns are structured. Because one thing he did tell me that I thought was interesting is if you have like a neuron, and like I said, you've got this area where there's proximal neurons before they branch, or proximal dendrites before they branch, and then they branch at some point. And it makes you think, like, if there's a bunch of synapses here and here and here, and those are all proximal synapses, it makes you think that there's a bunch of axons that are, you know, that are reaching from the bottom somehow, or from wherever they're coming from, and they're like going up through here and making synapses on their way through. And these are like these are the proximal ones, and they go to some area. And there's other axons out here that are making all of these distal connections, and maybe there's some organization to these. But Jeff has told me more than once this isn't actually how it works. It's not like there's a bunch of axons like growing up through this area and making these connections. And he hinted that had something to do with other types of neurons that were controlling that. But I'm going to have to ask him. So I'll take a note on that, because I think that's an interesting question that I've been wondering too. But good question, definitely.
Thank you.
Anything else? Okay. All right, I think that's it. Thanks, you guys, for joining. It was nice to have a hangout without any crazy people.
Right.
Last month, this guy kept joining. I had to kick him out twice. But anyway, take care. See you guys on the forums. Thanks a lot.
It's great to see you. Thank you.
Bye, guys.